Hi, today I'm going to talk about the off-policy learning. So off-policy learning, unlike on-policy learning, is basically uh, differentiating between the update policy and the action selection policy, in other words, the behavioral policy. So now we have the target policy and the behavioral policy. Let's ask why doing this is important. What kind of advantage can you get from this? So first of all, we know that the disadvantage coming from the on-policy learning is that there's a danger to be getting stuck into the local minima because we're generating experiences based on a single policy and then also trying to learn that single policy. So it's it's basically reinforcing to a specific direction instead of giving any possibilities of exploring other directions as well. That's not possible in on-policy. So this off-policy, differentiating between the two policies of this concept enables exploration. So that's the biggest advantage of off-policy learning. And also it's possible to learn about multiple policies while following one policy. Because, for example, in playing a game, for winning a game, if our goal is to maximize the reward function, which is winning a Go game, there could be multiple ways to which leads to victory. So we could also asynchronously use different agents who follow the single behavior policy, but each of them are trying to learn different policies. So, and the biggest formal point of advantage of this off-policy learning is that we can reuse experience generated from old policies. So when it comes to on-policy learning, we start with policy, say, Pi1. And then we do the generalized policy iteration, which is comprised of two steps, policy evaluation and policy improvement. So starting from Pi1, we improve the policy a little bit, which leads to Pi2. And then we evaluate that Pi2 and then improve it into Pi3 and so on. So Pi1 and Pi2 and Pi3 initially roots from policy Pi1, but they are treated as different policies, which means that in an on-policy setting, the current policy, which is Pi3, cannot learn from the experiences generated by Pi1 because the update policy and the behavior policy should be exactly the same in an on-policy setting. So we generate experience and then learn from it and discard and move on. That's the biggest idea of on-policy learning. But we know that a lot of implementations of this reinforcement learning, like, for example, neural network, could suffer from forgetting problems, which could be solved by learning from experiences, which is data generated by past policies. So to get that advantage of exploring from more data, it's like a batch. By off-policy learning, we're basically replicating the supervised learning environment, which smoothes the sequentialness in terms of the distribution of data that is specific for reinforcement learning. So when it comes to off-policy learning, when we deal with the values, the state value function, we have to go over a concept of importance sampling, which is basically, in machine learning, importance sampling Okay, and so in statistics or machine learning problems, a lot of cases we want to figure out the expected value for some probability distribution. But sometimes it's very difficult or even almost impossible to generate samples for that specific probability distribution. But there's other like proposed distributions, which is much more easier to get sample. So what we're trying to do with this importance sampling is to calculate the probability distribution of interest in the medium of another proposed distribution. And yes, so not too technically, the main idea is, let's say that the reward function for a reinforcement learning problem follows distribution of P. So basically, in terms of formula, it would be the multiplication between the reward function and the sum of probabilities of P. But we can't use P directly. We can't generate the data for some whatever reason. But we say we have data for another probability distribution, which is at least which has some similarity with the P, which is P is our probability of interest, and let's say that Q is a probability distribution that is more approachable, that which we have more access to. So we can approximate the p-value distribution in the medium with the approachable Q probability distribution by multiplying and dividing P by the Q probability distribution. Then the expected value becomes based on a probability distribution of Q, and the value itself now becomes the division between the old probability distribution and the new probability distribution multiplied by our original reward function. And so the division between the probability distribution of interest and the new probability distribution, proposed probability distribution, is called the weight, which is also called the importance. And that's why this is called the importance sampling. So this concept does have some analogy in terms of this off-policy setting, because I told you that now, instead of relying on one policy, we are relying on two policies, right? The one for the update policy, one for the action selection policy. So there's an analogy that, in the previous example that I said, the probability distribution of interest, which is P, now is our target policy, update policy. And the proposed policy, which is the more approachable, but not our direct interest probability distribution, which was Q, is the behavior policy. So what we want to do is to learn a target policy, but we're following another policy, which is a behavior policy. For whatever reason, we want to explore more, or we all have our specific criteria. But so now, in terms of the weight in this specific off policy setting, is now the division between the target policy distribution and the behavior policy distribution, which is the importance, the weight in this specific setting. Okay. So if we apply this off-policy learning to the Monte Carlo method, which is just trying out, like interacting with the environment, actually interacting until it hits the terminal point. Now, let's say that in some Monte Carlo simulation, we have time step of 20, right? So at time step 1, we will choose some action based on the behavior policy, right? And then that's the value for the denominator. And then the numerator, I'm talking about the importance, in the numerator, the value will be the probability of that action getting picked based on the target policy, right? So let's say that the behavior policy, I choose action A. But in the target policy, what would be the probability to choose action A? So we're trying to measure how much the target policy and the behavior policy matches, right? And by nature of the Monte Carlo method, because we are getting assigned an action and state based on the environment, right? We don't have control to environment. We could have control to our action, but basically we don't have control to the environment, right? We're getting randomly picked based on some underlying distribution. So, which means that there's so much randomness involved there. And since Monte Carlo is until hitting the terminal point, the randomness gets multiplied for t terms, which means that this approach will likely explode because of the variance, which theoretically could make sense, but in practice, using off-policy learning to Monte Carlo is a very bad idea. So what would be the alternative for that? The previous disadvantage, the biggest problem, comes from the nature of the Monte Carlo method itself, high variance problem. And as we discussed in the previous videos, the alternative for that is to implement the temporal difference learning, right? Which is just interacting with the environment for in the most naive way, just one time. And then, so that's what makes the algorithm grounded to the truth. But afterwards, after that time step 1, we just estimate. We're just relying on some estimation, which could possibly lead to bias problem, but at least it decreases the variance problem a lot. So also in this case, we could also apply the importance sampling to the temporal difference learning. So in this case, we only use one weight, which we don't have to multiply several terms, but still we have to kind of test. We have to figure out how much the target policy and the behavior policy matches. So if you see in this Bellman equation, so everything except this importance term is the same as the previous temporal difference learning setting for state value function. So the Bellman target is still same. So in this context, intuitively, this term means how much can we trust this target by assigning some kind of weight. If they match perfectly, then it will be 1, right? If they match perfectly, if the numerator and denominator are the same, the value becomes 1. So it just becomes a perfect setting for on policy, which didn't have this kind of didn't need to have this kind of consideration. But still, in practice, it is likely that the update policy and the behavior policy would not match. So this is not perfect, but still is much better than the Monte Carlo method with off policy. And all of this importance sampling the reason for applying importance sampling in the off-policy learning setting is because we were dealing with state value function. And again, we can see that there's an analogy to the previous video that we don't want to suffer from this kind of variance, which stems from state value functions. So now we instead apply this whole thing to the action value function, the Q value. So, and this is the most popular algorithm for off-policy learning, the Q learning. And to re-emphasize, now we don't need such thing as the importance sampling. And the interest idea of Q learning is that the action selection policy is chosen by, let's say, policy A. So our actual actions are determined by policy A, but we update our Q value function based on another policy. So what determines our action and what determines our update are based on two distinct policies, and this is still a valid Bellman equation, as you can see. In this equation, this action here, which determines the current Q value, AT here, is determined by the behavior policy, and the estimation here from the next state, A prime here, which is the alternative successor action, is determined by the target policy that we're trying to learn. So specifically for the Q learning, the advantage is that we are now, it's possible that we can improve both behavior policy and the target policy. So the target policy in Q learning is the absolute greedy approach, which is just getting the argmax of the Q value, which is basically just choosing the actions that return the highest Q value from the next state. That's for the target policy. And for the behavior policy, we're using epsilon greedy, which we discussed before. It's a sense like choosing sensible actions, which are still greedy, but we're here allowing some randomness, random actions based on probability epsilon. So we can behave in a way that we also explore more, not just concentrating into some, not just advancing into a direction that could lead to the local maximum, local optimal. So also, it's also this Q learning also satisfy the theorem that it converges to the optimal action value function. And this mainly comes from the fact that this R, which makes the algorithm grounded to the truth. If it only was based on our estimation, then it will likely diverge. But because we do have some reality factor in the equation, that's why we can stay ground to earth. The algorithm can actually approach to the optimal value. So here is the relationship between the full backup and the sample backup. Update based on the full width tree. And as we know, the sample backup is basically a tree that only advances to one direction. So when it comes, and the full backup was used in dynamic programming, and sample backup is used in temporal difference learning or if it gets extreme, it becomes Monte Carlo method. And if we have two categories, the other dimension of categories is which kind of Bellman equation we use, and what kind of Bellman equation does that calculate for. So if we use the Bellman expectation equation for the state value function, it becomes the iterative policy evaluation, which we saw in the dynamic programming. So as you can see here, the tree is the balanced tree. In fact, all of the full width updates based on the full width backup are balanced trees, perfectly balanced trees. So it's just getting the expected value given a state. We are calculating the expected value for all the successor states that are possible, and then just getting the mean of it and assigning to the value function, value state, the value function for the state of interest where we started from, the anchored where we started from. And we're doing iteratively, which makes the iterative policy evaluation. And TD learning is just from that full tree, the perfectly balanced tree. We're just choosing one trajectory, which is basically meaning that instead of getting the expectation, we're just sampling one of them, and then based on, and then we're advancing to that direction, which has, as I emphasized before, the advantage of TD learning over this full backup is that we don't have to know the state transition function or the reorg function, which in TD learning we could just learn model free without knowing the model. Well, the dynamic programming always needs the model based. It's a model based learning, right? And that was for the Bellman expectation equation for the state value function. And another category is the Bellman expectation equation for the Q value function. And here is the policy evaluation instead of the policy. We were just trying to figure out the evaluating some kind of policy instead of figuring out the optimal policy here. So if we apply the full backup to the Q value, it becomes the Q policy iteration, which is, again, now the only difference between the iterative policy evaluation and this Q policy iteration is that our interest is now on the action value. Otherwise, it's completely the same. And from this Q policy iteration, if we apply the sample backup, it's what we know as SARSA, which is the state action reward and state action for next state, calculating the Q value function based on that after sampling. And the last category is the Bellman optimality equation for the Q star. So now we're interested in figuring out the optimal Q value from our next state. So when it comes to, if we apply the full backup for this Bellman optimality equation, it's basically, so in an environment, if we choose an action, there's a probability distribution which determines the next state. An action, there's no such deterministic association between an action and the next state. A same action could lead to state 1 or state 2, and so there's a probability distribution there. And what we're trying to do with the full backup is that we are trying to put into account all the possible next states based on some action that we chose. And specifically, this Q value iteration is trying to, per state, let's say that our action leads to state 1, state 2. State 1 could lead to action 1, action 2 based on our behavior policy. And then from there on, we're trying to get the maximum Q value. So our interest is to figure out the action that maximizes the Q value from the next state instead of our current action made state. And then, so state 1 could have its maximum trajectory. State 2 could have its maximum trajectory associated with some value. State 3 and so on. And then we're trying to get the average of it. And then that average will be assigned to the Q star. And but the problem is that then we would have to know the model again, right? We would have to know the reward function and the transition function, which is unrealistic in real implementation. So that's where the sampling dives in, which makes the Q learning, which is we sample by our action instead of considering all the probable states, multiple states that could possibly occur. We don't care about it. We just sample one state that is caused by our action. And then from that determined state, we try to figure out what might happen, which action would maximize the Q value of from on state, next state plus one, T plus one, and then try to maximize it.